Numerical differentiation using least squares. So many engineers preferred curve fitting over interpolation because of its robustness, against noise and outliers. The least square method in Module 3 provides a more thorough example. So recall the function f of x here. Okay, so the polynomial, okay, given the coefficients x, a0, a1, and am, that can fit the n plus data points. Okay, so you have the data points up to n. So now if n and m are equal, so then this method is what we call the interpolation. Okay, but since they're not equal for the least square, so we call this one the curve fitting. Okay, so polynomial coefficients, these values here are polynomial coefficients. Okay, in module 3 we discussed about line, quadratic, and second order, or even the point function. Okay, to understand these polynomial coefficients. So however, in this module, those coefficients can also represent an exponential function. Okay, hence the form f of x is determined beforehand based on the experiment for which the data is generated. So we have this fit. Okay, basically we have the data points, y, sorry, the y data points minus the you have the function f, okay, with the coefficients of the polynomial, and then you estimate the x of the data. Okay, so basically this is like a prediction of your y, okay, given the function f. Okay, so then take the difference. This would mean an error. Okay, you can think of it as an error, or we commonly term this one as residual. Okay, then the least square fit simply minimizes the function s. So we minimize the error. Okay, so we can call it the square error. Okay, so this is the sum of the squares of the residuals. Hence, we wanted it to minimize, so therefore we need to take the partial derivative of s in terms of the coefficients and equate it into 0. Okay, so as much as possible close to 0. Okay, so generally these functions are nonlinear in coefficients ai, may be difficult to solve. Thus, to make this linear, a fitting function with a linear combination of specified function fj of x is chosen. Okay, so you can go back to the module 3 polynomial fit. So basically the idea is simply with this, no? So you have the function f of x, okay, where f of x is the m degree polynomial function. So you have this. For example, the first one is 1, the second is x, and then the other one is x squared. Okay, so there are other ways to express that one. Can be instead of x squared, no, polynomial, you can use trigonometric identities. You can also use Taylor series and other series, no? Okay, so recall the formula polyfit. So we have here the rows, the Gauss pivot, okay, and then the polyfit. So we need this from module number 2, okay, for the function of polyfit. Okay, so we would like to fit, for example, in this case we have the points, we want to fit this one into a curve. So you might be tempted to use a straight line, which is also a good representation for this case. Okay, and then we have the um, this function here to predict the polynomial coefficients. Okay, sorry, using the polynomial coefficient we use to predict. Okay, so for the polynomial with the n degree, so you have f of x. Okay, so it's quite familiar to us, this very simple polynomial. And then we use the standard deviation to choose, which one, which of the polynomial n. Okay, because we can choose 0, we can choose 1, 2, 3, 4, or 5, as the best fit curve. So as I said in this example, we can either use a straight line, or maybe you want a little curve, okay, or maybe a third degree if you want. Okay, so basically that's the n. It can be 0, 0, but it's not, cannot be 0. Okay, 1, 2, until a certain number. No, basically the total number of points. Okay, number of points, number of data points. Okay. Okay, and so okay, we have here the standard deviation, and then the derivative. In this case, we have the derivative. So basically, very simple. You have the derivative, the function here, okay, which is the line that fits the points, the data points, and then take the derivative of that one. Okay, and it's very easy. Okay, so this one, we take the derivative of this one, and we can express this one as, okay, this equation. Okay. Then given f, the first derivative, we can easily get the derivative at any point. Now in this example, we just take the first derivative, no? Okay, so if you want to go higher, I mean you want to take the n, or um, the, let's say, um, the the or let's say if you want to take the third derivative, no? Okay, so just simply get this one. Okay, get the you can actually code that one, no? Because it follows a pattern. Okay, you can follow a pattern. Actually, you can take 2 times of this code here. Okay, so the way we express this one to here, so we use this function here. Okay, so if you want to take the second one, so you can maybe take twice of this. Okay, so that's it, that's the derivative. So if you want to take the derivative, so most of the problem will ask for, okay, what is the derivative of these points? You know, if you have these points, what will be the derivative at a certain x, let's say 5, or maybe 4.25. So what will be the this point here? Let's say we have a point here, so we want to know what is the point there. Or if we have from 10, okay, from here, more than 10, 11, if we want to predict, no, so we know that the straight line goes this one, so what will be this value, what will be this value here? Okay, so maybe we want to look for that. Okay, or sorry, straight line, what will be the value here? So this line here is what the f of x is, no? It can be curve or whatever curve expressed by the polynomial function. Okay, so that's it, the first part. Okay, there are 2 steps. The first step is to fit the data points, okay, using the least square method, and then take the derivative, or the second step, get the derivative of that polynomial. Okay, so the polynomial is expressed by the coefficients, then we also use the coefficients to determine our derivative. Okay, and then we evaluate this one at point x. Okay, whatever the problem is looking for. Okay, that's it.